Thanks, Kellen, and thanks everyone for sticking around to the end of the day. So 53 years ago next week, Apollo 15 landed near Hadleyville. The astronauts did some exploration science. Then a few days later, they left the lunar surface. And this presentation focuses on what happened shortly after that. My co-authors are Ben Astacio and Dana Hurley from APL, and Rich Vondrak, who is retired from NASA Goddard. I'd also like to acknowledge support from NASA through the Survey Leader Team and the Viper COI program, and computational support from the NSF Access program. Apollo 15 was one of several Apollo missions that deployed instruments on the lunar surface that were sensitive to exospheric gases. Those included naturally occurring gases, as well as those released by anthropogenic sources, so from spacecraft outgassing to astronaut backpacks. This is an LROC image of the Apollo 15 landing region. You can see the lunar module. You can see the tracks where the astronauts trekked out and deployed some instruments. Those included the cold cathode gauge, or CCG, which is the little guy that you see attached to the leg of another exospheric instrument, the superthermal ion detector. Both those instruments and the others operated for several lunar days, but we focus here on the brief interval of time following the liftoff of the Apollo 15 Ascent stage. So we take a look at the CCG data and see if we can say anything about what that tells us about lunar volatile transport. This is the snippet of data that we're interested in. So on the left, you have a chart that shows gas density as a function of time. Note that the CCG did not measure composition, and so the density there is in terms of equivalent nitrogen. And so the instrument is sitting there, it's slowly outgassing. At the instant when the ascent stage lifts off, the density skyrockets, the instrument saturates, it remains off scale for around 90 seconds before the density starts to decay. There's a mystery bump a few minutes later, which may or may not be real, and then the density continues to decay back to the pre-liftoff baseline. In the next few slides, the results I'll show focus on the first few tens of seconds after liftoff. So the spacecraft initially rises vertically, it then tips over and then continues its journey to meet the command module and take the astronauts back home. This was a really fun opportunity to test out some of the models that I'd previously developed. I'll refer you to the paper for the details of the model. I'll just mention here a few of the key assumptions, which are firstly, that we only model one of the species involved. We assume that the entire exhaust is composed of H2O. In reality, it's about a third. We assume that water molecules that strike the lunar surface fully thermally accommodate and are diffusely scattered, and we assume a desorption activation energy of 0.7 eV, which at this latitude and this time of day means that water molecules have a negligible residence time on the lunar surface. And in the next few slides, you'll see some plots that look like the one here. So what you're looking at there is the density at ground level and in a plane that intersects the landing site and the instrument location, and there are dots indicating the spacecraft trajectory. So with a three-dimensional model, we can look at density as a function of distance from the lunar module, or from the lunar module descent stage, in this case. And the different colored lines indicate density as a function of distance at several different times. And so several things to note. First of all, we see that within seconds after liftoff, the density does rise to several orders of magnitude above what the instrument could measure. So that at least is consistent with observations. Something else that you'll note, which we can't necessarily tell from the data alone, is that there's significant asymmetry in the distribution of the gas about the landing site, and that is related to the pointing direction of the thrusters. So initially you have that vertical rise, and so the gas is more or less symmetrically distributed. And then as the spacecraft tilts over, you can see that most of that material is directed downrange. And so that's why we see that in one direction, the density is orders of magnitude higher than in the other. We're still running simulations. One of the things that we're watching for is when does the density fall below the saturation level? When can you see that decay again? So the lines here go out to 18 seconds after liftoff. And so you'll see that at 18 seconds, at the position of the cold cathode gauge, the density is initially high, it fluctuates a little, it begins to decay. At 18 seconds, it's still an order of magnitude above saturation levels, but it does seem to be falling. And so we're keeping an eye on that. And if it falls below saturation in less than 90 seconds, that may be an indication that we need a surface that holds on to that gas more tightly. There are different ways of measuring exospheric density. So you can be a cold cathode gauge or a mass spectrometer. You can sit on the surface, wait for molecules to fall into you. Or you can be like LAMP or other instruments and look through a column of gas. So what we wanted to do here was to give you an idea, was to give you a different view of this liftoff scenario. So what you're looking at now is a plot of column density 16 seconds after liftoff. And so we're looking down at the landing site. The colors are the number of molecules in each square centimeter vertical column above the surface. The black and white dots indicate the spacecraft trajectory, and the pink dot indicates the location of the cold cathode gauge. And so again, things to note, the densities here are elevated. They're several orders of magnitude higher than typical exospheric column densities. That's true everywhere in this 750 meter region around the landing site. It's especially true downrange, where most of that gas is directed at this instant in time. And so I wanted to show this for several reasons. One, to point out something that we haven't looked at, but which might be interesting, especially to some of the plasma modelers out there. There is reason to think that solar-wind interactions with a dense expanding cloud of gas like this can give rise to some interesting observable phenomena. So for instance, the side instrument on Apollo 15 did observe this approximately 8-minute disturbance in magnetosheath ion flux that was correlated with the Ascent. So something we haven't looked at in detail, but I did want to throw it out there while I have everyone in this room. So we're still continuing to run the simulations. They're expensive, but they're also tractable. So every 2 seconds takes about an hour of real time. So it's not a trivial simulation, but it is very tractable. We're continuing to run it, and we think we can get some constraints on gas surface interaction parameters. Some next steps might be to include some of the other volatiles that we know were present in the exhaust, and maybe to investigate a little more deeply those potential interactions with the solar wind. And I wanted to leave you with some thoughts for future missions. Modeling like this is only possible because of the detail and the care with which things like the combustion products and the trajectory details were documented and preserved. And so this is data that we sometimes think of as engineering or operational data, but it really does have science value. And so for anyone planning a mission, I encourage you, and I've been thinking myself about what the modelers 53 years from now would want. There are so many uncertainties associated with the lunar volatile cycle, and any time we can take some of that uncertainty away by looking at what happens when you have a very well-characterized, relatively well-understood source, that's a worthwhile experiment to do. It's also an experiment that's only possible if you have exospheric sensors, and I think there's a strong case for exospheric sensors of different kinds at different locations. They can tell us a lot about the lunar volatile cycle. And I'll leave you with this short video of Apollo 15 lifting off the lunar surface. You can see the shadow of the ascent stage. You can see it moving over the astronaut tracks and deployed instruments. There's the descent stage. The camera pans up, and we head for home. And so you see the rocks. You don't see the exosphere, but it's there, and it's very well worth observing. Thank you, everyone.